Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is Fundamentals of Motor Protection. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is David Beard, Relay Applications Engineer. Also, to assist with the question and answer session, we will have joining us Abel Gonzalez, Applications Engineer, and Sugosh Cooper, Relay Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, David.
All right, thanks, Mike. Hey, I would like to thank everybody for joining us today. I know it's getting close to the holidays here, but I really appreciate you guys' time and everybody joining us today for these webinar series that we put together for you guys. Let's get started here. So what we're going to kind of go over is a little bit of the basic overview of how the motor works. We're going to view over a standards glance. So basically a couple of the standards that we're going to kind of talk a little bit about, some of the information in there that relates to our protection topics. We're going to talk a little bit about the motor failures that can happen in motors, things that we need to know as far as nameplate information and certain types of manufacturer information that we need for settings and to allow us to put together the protection principles and make sure that we're making our protection schemes very sensitive. We want to do types of protection used. It's going to be we'll kind of go over a few of those. There's so many for motor protection, but with the limited amount of time we have today, we can only cover a short duration of them. And then we'll go through a summary and a Q&A like we always do at the end of our webinars. So the basic motor overview, we're just going to kind of give you an overall of how the internal workings of the motor work, or not. I'm sorry, the internal parts of the motor we're not going to really discuss, but what we will talk about is the overall concept in which the motors are used here in the industries. So motors are used in many industries and they serve a purpose for many applications, as you can see here. What was really interesting to see is a lot of these manufacturing plants, and just as I was viewing and researching what all uses motors, and it's almost just anything that can have any type of rotating machinery or any type of assembly line or system uses motors. And what was really interesting was, we know the chemical plants and recycling, we have food manufacturing. Metallurgy was something I thought was really interesting. The pulp and paper is a very heavy industry up in the north part of the U.S. And then also manufacturing plants that manufacture induction motors was pretty neat to kind of see that. I've always wondered if they use their own motors that they create on their own assembly lines, but who knows? But you can also see, looking at this whole range of different ways that motors are used, you can see why that 80% of the electrical energy produced in the world is used to power these motors. Since induction motors are the majority of this percentage, we will be discussing this type for the most part of this webinar. So we won't really get into the synchronous type motors. So we do have a couple types, and I know I said we're not getting into the synchronous type motor, but we are going to have to, differentiate the two. So in the induction motor, once it's energized, it'll create a magnetic field in the stator winding at this system speed, and that speed we're talking about is the 50 or 60 hertz, and that depends on the location where you are located in the world. So the stator winding magnetic field will induce this voltage into the rotor winding, thus drawing a current from the system. So once the rotor is up to an asynchronous speed of the 50 to 60 hertz plus or minus the slip frequency, it will remain there until either it is shut down by system personnel or if a fault occurs. I'm taking off. Apologize for that. So the synchronous motor kind of went ahead a little bit there. So the synchronous motor piece is the same rules apply in the synchronous motor, and what you'll see is that it gets magnetically locked to the rated frequency. And the reason, the way it does this is on the rotor, it actually has a winding that's attached to the rotor that gives DC excitation. So it basically turns that rotor into an electromagnet, and it'll magnetically lock to the rated system frequency. So there's no slip in between there, just like the induction motor has. So in this diagram, we're kind of providing just an overall simple look of what the construction of electromechanical system would look like. So we have the power supply piece. Of course, it's power in the motor, and then the motor is attached to the load. And the power supply is designed to deliver power at a specific frequency. So this is defined by the generator or the drive supplying the power to the motor. Most often with the direct bus feed motors, this frequency is either 50 or 60 hertz again, and depending on your power, which is dependent upon the power convention in your system or in your region, I mean. So the supplied voltage is going to be fed through the three-phase leads on the motor stator winding, as you see here. So based on the stator winding design, the rotating magnetic field is created. The speed of this rotating magnetic field is directly proportional to the number of poles created by the winding. So we have frequency. It's actually it's the rated frequency. It's coming into the motor, and then the motor is starting to build up the asynchronous speed internal, and then now we're trying to overcome the motor torque and the load torque to allow us to start spinning the load, right? Or spin, or what, pumps, or whatever that load could be. And so this synchronous field, I'm sorry, I got off there a little bit. So since the rotor circuit is effectively shorted with the conductive bars internal, we're actually drawing a current. Current begins to draw and flow into the motor. So we have the torque from the load coming in, and then we're also consuming power from the system, and then regulating the motor with using the voltage is also, resulting we're drawing current from the system as well. Now, if the rotation, as long as the torque that's produced by this interaction is greater than the torque required to turn the connected load, then the shaft will begin to rotate, right? So sometimes if we're not overcoming this torque piece in the motor or the torque of the actual load, then we're going to not be able to turn this load, and it'll be too much for this motor. If the load is changed in such that it is greater than the torque, then this guy could slow down or stop. So we're trying to regulate, and we're trying to make sure our load doesn't exceed the limitations of the motor itself. So we do have a few things that can go wrong with the motor. Bad lead terminations. This is mostly a human error, and is very important to double check or verify the motor terminations are torqued and correctly installed per manufacturer specs. We also have electrical unbalance, which could be the supply voltage is unbalanced coming from the utility or generating source which feeds the motor. We could also have bent shaft, bent rotor shaft, and this can be caused, excuse me, this could be caused by extremely high loading or extremely high heat. We also have rotor damage. Rotor damage is the unbalanced conditions or results from bearing damage or poor workmanship. A lot of times you don't ever, you come through and think that a lot of the things that could go wrong with the motor is electrically wrong, but sometimes workmanship plays a big part in that as well, as making sure that the manufacturing, the way it's manufactured is done proper, and just manufacturer defects can actually can make motors go. Can damage motors and make motors not run efficiently. So we have rotor damage. Rotor damage, I just went over that one, sorry. So stator damage will be, so an example of stator damage will be single phasing in the motor. It could be due to the loss of one phase of the three-phase supply, and this could burn the stator winding up if not taken care of with the proper protection. And now we have lamination shorts. This can also be caused by overloading. Overloading brings excessive heat, and excessive heat will break down the insulation inside these laminations. And then we could have open circuit, manufacturing errors, or a fault in the winding that could burn a conductor open. This could cause the motor to stop. And then the last one will be, bearing damage. Bearing damage is a common failure, and because it has so many moving parts, and it's encased in a lubricating medium, but it still takes a lot of abuse, and it also holds the weight of the rotor shaft as well. So, you can see why that would be a very high. And then you also have other conditions, other causes, for the wrong size wiring and poor workmanship and so forth. We'll talk a little bit about the standards. Remember, I was saying the standards at a glance. Okay, you've seen them. That's it. We're going to the next slide. No, we're actually in this. So I just kind of want to run through those a little bit. The webinar is not in this webinar is not intended to list all the requirements that we're going to go through in these standards, but these are a few that I did use some of the information from, which is very important, and it does apply to most of the common motor installations that affect the power system design. These standards are thorough, and they give recommendations and examples of how to apply different types of protection for different applications as well. So these are good resources to have and be able to get a hold of. Next, we'll talk a little bit about motor faults. And motor faults can be present when the motor is starting, or whenever the motor is in full operation and a mechanical issue shows up in the motor, or there's a fault in the power supply. So as you'll see here, this is table 2 from the IEEE standard that I previously mentioned in a couple slides back, and you'll see that it shows the most common types of failures for different types of motor designs. So when you come in, looking at the chart here, you'll notice just as as they have labeled out here in this IEEE standard, you have the bearings. So you have for induction motors and synchronous, were the two are kind of more prevalent in the industry. Of course, the induction motor, and then it kind of gives you the modes of failure and what the as you can see, the bearing failure, which most of them have, with all the moving parts and so forth, is kind of at the top of the table here. But it also, what's really nice is it kind of allows you to see what type of protection can be used for properly detecting these failed component issues here. So as you can see, the windings, we also, for winding issues, we have multiple array of of different elements, and as before, there's so many to go over, so we won't be able to do that today, but we will hit the major ones here. So this one, I just want to kind of show a little bit about what these faults look like. So this image just shows a little bit about what a single phase fault would be. With a fault, this is a fault in the winding of the stator, and you can kind of see the discoloration of the insulation in the leads here. So it very well could have went phase to ground in here in the system, or it could have been one of the phases had dropped loose. This could be one phase. We just don't know from looking at this example here. The one on the second image here, you can kind of see where it's a turn-to-turn short, and it's damaged the insulation that's actually around these windings that are going inside this cage here. So, but this is, to catch things like this, especially if they're internal to the machine, the differential protection would be good to use against these types of faults. Bearing failures, with this being at the top of the list, you can kind of see, as this image here it just kind of, when you start looking at this guy, it just seems to be that there is something that has gouged the external piece of this bearing, and it could have been something that's broken off internal to the motor. It could have been something that wasn't aligned properly, but something has really took a hit inside and really gouged the inside of this bearing. So that would be a replacement job, of course. And then this guy for the second picture, I mean, man, this is a nasty hit right here. The case has come off. The bearings are just totally destroyed. Could have been done to overheating, could have been done to vibration. And this thing right here, all I have to say is that's not going to buff out. That guy is a full replacement, of course. So rotor faults. So this one was kind of interesting. So when you look at it, the rotor faults, you can kind of see this fin is a little bit out of place here. And this one was due to erosion sitting outside, and then a little bit of vibration is starting to crack, not just this one rotor fin, but multiple rotor fins here. There's a crack here and a crack here, as you can see. So it did take a pretty good toll on it. But, the fins seem to have started moving also, because you can kind of see that this guy's bent a little bit, so it could have moved due to the centrifugal force of the rotor moving itself. So there's a lot of causes, a lot of things that could go wrong, and this could also hamper the rotor from turning smoothly inside the stator winding. And then this guy here on this is pointing out brazing. So when the excuse me, when the shorting bars are being brazed together, they're actually looking at this cold weld here. So it doesn't look like a smooth melted metal weld. And that's where we kind of marked it for a brazing issue. And you can tell from this side as this being a good weld and this being a cold or soft weld. And this can cause issues. And you can find this out by testing and with different pieces of equipment. So motor faults, as we all know, are very costly. So why are they costly? Well, it's because it's motor downtime. When the motor's down, the money's not being made. And a lot of times that also entails a lot of other things. So now we're starting to chain together the scenarios that come into place when the motor's down. So now we have to repair and replace this motor. We have to, and this takes a lot of time to send these big motors in for repair and have them repaired, or we can have them repaired on location. It's just, it depends on outweighing the cost of tearing down the old motor or replacing it with a new one. So a lot of tools also need to be brought on location just to even do a repair or replacement, and shipping costs are costly. So there's a lot of little additional costs that just get added into this. The process downtime, what is the motor tied to? Um, if the motor's down, the process is down. Are you able to divert the process over to another part of the plant and still keep it running at a lower output? These things have to come into mind, and what we can do when this motor goes out. Personnel scheduling issue. We just to get people to come on, during depends on what time of season it is, because a lot of times a lot of plants are doing maintenance schedules during specific times of the year, low load times, and personnel scheduling is a little difficult when everybody's busy and everybody's scheduled out. And then we have to add the additional factor that we're all very well aware of now, which is COVID. So when we have this added piece to the mix, it's makes this personnel scheduling very difficult, and also raises the cost because we're having to do sanitizing out in the field. You're having to check personnel before they come on location. So this adds a whole new cost to motor faults or motor failures. And then also, in the end, it pretty much eats up bottom line on the profits, and everybody suffers in the end on this one. So it's just we try to minimize this motor downtime. So here are some things to know when we're actually going for trying to set this information into these protective functions and in these different relays. And one is full load amps. What we need to do is we need to find where it's printed or some type of manufacturer documentation. And most of the time, as you can see here, you can see that there's the full load amps is marked. I've got a couple images here, just some examples of where this information lays. And everything is printed on nameplate, full load amps. And then also, if you notice that there's a dividing line here that shows for the two different voltage levels. So at the 230 volts on this example, it's the 21.4 amps. So at a higher voltage, you get the lower amperage, right? So you get on this nameplate is showing us dual voltage as well. And here, and some are laid out very well. And a lot of times too, when you look at the amps, they might not say full load amps, which is, excuse me, is what you can see here on this nameplate. And oh man, I'm just going crazy here. I apologize. Okay, next one is service factor. So the service factor is another value that we need in the calculations for motor protection as well, also with the thermal limits. So the service factor allows us to how much over 100% can we run the motor and it still function at the specified power factor. So the service factors are labeled. All of them are labeled on the nameplate information as well. Each one needs to be looked at. And even in some, I was looking through some relay manufacturer information, and some will dictate that if you have a service factor of 1, then it's they automatically tell you to calculate it at 1.05. But you need to look at the manufacturer literature for that. So each there are some different cases for different scenarios, and this would be one of them. So I would definitely look at whichever relay protection you're going to apply and see what they're going to do, what they recommend to do for a service factor of 1. The locked rotor current. So this value is also on the nameplate, but it's not as easy to decipher as the other information. So now we're going into codes. So this code is a letter that's for the locked rotor. It should be a KVA code. And the NEMA specification defines the locked rotor KVA in per horsepower. And this is an excerpt here from the NEMA guide MG-1. And you'll see that where I've located the code here, G, which is actually on this nameplate, I'll come down and cross-reference this to G in the NEMA guide, and it will tell me what the KVA per horsepower will be. And this is how I'm going to get my locked rotor current. So you can find this guide online. You can find this through the Standards Commission, but all these are in codes. And what I will say, one thing to this too, is there's a lot of information going on in this nameplate, and it's very busy. And just make sure that you're reading correctly the correct code. If you're not reading the correct one, and let's say you come over here and get off and you're on B, then you think this is it, and you end up cross-reference B, and you end up with underprotecting, you know, the motor itself, and or you could cause false tripping, or you could cause, you know, all types of different events. So you want to make sure that you are reading this nameplate information correctly, and you are cross-referencing these numbers, because there's a lot going on in these nameplates. Other information that we can get to, and it's most of the times obtained by the motor manufacturers, is the permissible continuous allowable temperature rise. So what is it allowed to rise in temperature? So sometimes it's a 10-degree rise to be able to keep your insulation levels still in operating conditions and not damage the motor. We also need the acceleration time. If you can get that information, if you have old motors that you know, don't have any nameplates, or all the drawings are gone, or you know, all the information's out, then some of this information you're not able to get. So the rated voltage, of course, is, you know, is on the nameplate as well. If not, you know, you should have some drawings and schematics for that information. And then two, the other important item is the motor thermal compatibility curve. And what this guy is he allows us to see where the thermal capability curve lies within the starting currents of the motor itself. And this is very useful, because I will show you here in a moment where we really need to utilize this information. Types of protection. We're going to go into our protection types now. So the phase overcurrent protection, this will be the first one that we start with. Most of the time, the motor is at the end of the line, right? So after all the feeders, the motor is the guy on the end of the line. So we need to make sure that that we set the it must be set above the starting. The instantaneous overcurrent needs to be set above the starting current, and also if it needs to have some inherent small time delay in there. But most of the time it just sets, you know, we can just set this value above the starting current, because if the motor doesn't start properly, then what happens is either it doesn't start and we have no current and no trip, or we also have the motor starts and something's wrong and our current just skyrockets. So we need the instantaneous level there for our protection. And also for short circuit protection, in where the fault current can be the highest at the terminals of the motor. We also have, so the next one will be time overcurrent. And this just means that the trip is inversely proportional to the fault current. So what allows us to do is this allows us to coordinate the time overcurrent elements with the thermal model. And it also helps, this helps with protecting the locked rotor, and also with the starting component decay. So when I told you about 3 or 4 slides ago that there was a motor compatibility curve, this is what I was talking about, is we can take this curve that you can get from the motor manufacturer, and then you will take what relay manufacturer time curve that you have that you wanted to use or compare against, and overlay these guys. So this will allow you to actually see the coordination between the thermal curve and your actual time over current curve for the relay itself. And this helps a lot with, they used to call these little skins in the time over currents relays, and you could take them and they were so thin you could just overlay them on top of the machine or device. You know, these motor thermal curves, you could just lay them on top of it and see through them. So that was also really nice. You know, it just, those are the days of paper. Oh man. Okay. So the 50G, so we have ground protection, and there's a couple different ways to do this. So this is the preferred method to do, and the CT provides a magnetic summation of the three currents here. So the secondary output of the relay will be 0 if everything is balanced. This also provides a better reliability during across the line starting by eliminating the false startup currents resulting from the unequal saturation of the CTs during startup. So the limitation to this is that all three of these conductors may not physically pass through the CT window. So when you have that scenario, then you need to come, here's application number 2. So how can we get out of that one? So what we do is we have multiple different ways to do things. So now we can take the CT, or not the CT, we can take the relay and mount it. We can set, we can connect the CT in the residual circuit of the phase CTs. This is just like we have here. The physical size won't be an issue because we're connecting in the circuit, and we don't actually have a CT that we're going to be running through with each individual motor or the return. And then also we need to make sure that we set this thing above any false residual currents that can result from unequal performance or high unequal offset starting currents. Prevent the probability of false relay operation as well, as long as the CT burdens are limited to the voltage developed by the saturation of the CT. So that gives you that second option. The next option we have is our next element is differential protection, and the differential protection is very similar to that of generator protection. Both ends of the motor serves as the primary winding of the CT, as you can see here, because we're going to, the way the CTs are tighter on the primary side of the motor and on the neutral side of the motor as well. But the neutral, the CTs on the neutral side will be the same ratio as the CTs on the phase side. And the connections will be made inside the neutral connection as it's shown. So you can see here where the CTs are lying inside this connection. So on a drawing, this looks a little, looks very easy. But what I want to show you is the actual what it looks like. So this one is gonna, you'll notice this is the neutral bar I was explaining here. A little bit different diagram, but the neutral bar is still tied together, and you can see this neutral bar here where all these returns are being tied in. And this is the same return cable that's coming back from the motor, and this is just showing the actual cable coming back through the same CT. And this, and of course the summing CT itself, and these CTs are going to sum the current flows of the motor winding from the motor going into the CT tied to the neutral and coming back, and you can see that connection here at the bottom. So you can see that the motor leads are going into the motor, back into the motor winding, and then coming back out to return and being tied to the bus bar, which you can see here. Excuse me. So how does the differential current work? So the basic principle of how differential protection works is if we have within our protected zone of our CTs, we have our motor, and then we have neutral and line side. And this is just an example, just kind of showing you how the protection goes. So as currents are flowing from the motor, currents are being pulled. I'm sorry. Excuse me. So the motor's drawing the line, supply from the line. We get an external fault outside of our protected zone. Then our CTs are still drawing current, and everything is looking good, right? So everything is moving. We don't have any type of differential current because our fault is actually outside of our protected zone inside of the motor relay. So we will not see any currents that are going to add up across the relay, therefore we get no trip. So what if that fault was inside the protected zone? Well, the same scenario is going to apply, but it's going to be a little bit different because now we have the line is actually feeding this fault that's inside of our protected zone, and now our currents are showing differential current around the relay itself, because now we have our currents are adding up since they're coming in and feeding this external or this internal fault. Oh man, I'm telling you. Yeah, so not getting a trip. So now we move on to phase reversal. So when starting a motor, it is good practice to make sure that you're connected correctly so that the phases are not reversed. Because this can cause catastrophic damage if the motor's rotated in the wrong direction. As you can see, it's just this is some heavy duty stuff. But the relay can detect for this simple application, and this will help verify the phase rotation measured compares to the phase rotation setting in the relay. So right now we're looking at phase rotation with ABC going counterclockwise rotation, and it's going to give us all positive sequence. So if I reverse 2 phases electrically, then our positive sequence goes down to nothing, or very low value, not to nothing, very low value. And then now we're going to get a 1 per unit value for what we had in positive sequence is now going to equal that of negative sequence. And now we're electrically rotating clockwise rotation instead of, and we're still wired physically for a counterclockwise position. So this thing can get phase reversal protection is very easy to set. It's just an ABC or a phase rotation setting, and the relay usually takes it from there. Relay locked rotor protection can be a loss of supply in one of the phases. We can have mechanical problems. We can have a low voltage supply, which doesn't allow the motor to overcome the load torque, or we can have excessive torque, which can be kind of almost a mixture of the two. If we have low voltage supply, we could in turn create excessive torque, right? Or we can have something that the motor's tied to and it's not able to overcome, actually able to drive that load and get it moving. So during startup, as expected, though, there will be large current draw from the supply, and this will cause extremely high temps inside the motor. But until the motor gets up to speed and has began to move, that's when it'll improve its cooling, because the fan that's internal to the motor needs to be moving. The locked rotor protection is basically protected with an overcurrent relay with an adjustable time delay. And this relay will trip the motor when it exceeds its permissible starting time, but it doesn't need to do it before this. I'm sorry. It exceeds a permissible starting time, but before the safe stall withstand time. So also this element also needs to be tied to a restart inhibit, which needs to be set, because you don't want to constantly keep pounding this guy. Especially if you got a locked rotor condition. You just, if you have an issue, you don't want it to keep doing it. So if you look at the graph here, it kind of gives you an idea of how to set this guy. So, right, so the starting current of the motor is going to be, what do we say, 6 times, and it's going to be 6 times full load amps. It comes in here, and then it's actually going to be set for a duration of time before it starts leveling off. So you want to make sure that you set your relay current setting high enough that we cover for this current, but also we need to add a time delay to allow the motor to level off. If this motor doesn't level off, then this current's going to keep going, and it's going to start getting into the relay time delay, and then the relay is going to trip. So it'd be taking this scenario and moving it up. Mechanical jam protection. Serves to protect the motor during sudden rotor blocking and allows for a quick motor shutdown. Now, the motor can stall when the motor load torque exceeds the breakdown torque, and the speed of the motor goes to 0 or to a point below rated speed. But, chaos can rear its ugly head, of course, and sometimes there's a lot of conditions that can take place during the time the motor seems to be doing fine. But when the issues arise, you'll know that it's like in the image, the shaft can break off and twist, or we can lose the prime on a pump or shear the drive pin. I want to put this piece in here to just kind of show there's a lot of little mechanical parts, and even with this being on a generator is a good example to kind of see what else can happen. Not only will the drive of the shaft, spin as well, but also this has got a huge knuckle, so there can be a lot of mechanical jam within here. So it's making sure all the movable parts work. So here's an example of the lock rotor protection. So it is, like I said earlier, it's basically just an overcurrent relay with an adjustable time delay, as we saw. So the relay will trip the motor, and then when it exceeds its permissible starting time, but before the safe stall with stand time. So let's see what happens. So now in this example, we're actually going to bring power in. So we're bringing the power into the motor. And once it's supplying the power supply, we're getting current. We're actually supplying power to the motor now, and then the motor tries to turn, and apparently we have an issue with this guy. So the rotor's not going to move because the contact's closed, and it's calling for the motor to turn on, but the motor's just stuck. So guess what? There's that cost savings again, right? It's all that money's just going all over the place because you're going to have to pay for a new motor, or you're going to have to spend time to troubleshoot it. Load loss protection. So we can set this, the low set forward power relay, or the element, is technically what is monitoring the load, and this will be possible to use. This will help protect against the pump from becoming unprimed or stop a motor on an assembly line because a conveyor belt broke. This type of protection will also need to be interlocked with the motor starting device to prevent operation when the motor is tripped, because this can prevent a motor start as well. When starting a motor against a very low load, then this function will need to be inhibited long enough to allow the motor to get to 100%. And then the power is more accurate representation. So when you're using the power load loss for the power, it's actually giving you a better representation of what that loading was before and after an event, should an event occur. And then you can also use undercurrent elements for this type of protection as well. And what the element will do is trip or alarm, depending on how it's set. And the current levels, once these current levels have dropped below the set points. Now, this element will need to be set above the expected no load current, but less than the minimum expected current when the motor is operating normally. So most relays will have this element in per unit of FLA, which will be full load amps. So load loss protection. what we were explaining earlier. This is a good little example here. And what we're doing is, again, using the same model as we did before. We're supplying power to the motor. We have we're supplying the proper frequency and supply to the motor. The motor's building up speed. The motor's actually taking on the load. So now the load is spinning and we got our torque and everything's looking good. We're drawing power from the system. We're regulating the motor itself, and all of a sudden the shaft breaks off and we don't have load anymore. So we have completely lost this guy. The motor needs to be shut down, and with the load loss protection element, we're not seeing that load. It has went to zero pretty much on this scenario, and we should receive a trip to trip this motor. So under voltage protection, this is a pretty common sense kind of go around. Under voltage, if we don't have the proper voltage, we're not able to start what we need to start. But the low supply voltage to a motor can result in a loss of speed, and it could draw heavy load currents. So preventing from reaching these rated speeds as well. So if the motor, let's say if the motor was already running and runs into an issue, then it could lose speed and fall out of sync. So you can see here that we have a low voltage scenario now happening. So we're delivering power to the motor, and of course the motor can't start because the power is not it's not up to where it needs to be. And most relays kind of look at an 80% to 100%. I think 80 being the low end. So from what I've been working through. So it does take a minute to kind of get this troubleshooted a little bit, but in turn, again, it still kind of costs you money because this thing's down and you're having to troubleshoot your cabinet now, or your power supply. Also, if your motor runs into loses power, the high inertia of the load can also drive. High inertia load can also drive this as well, so it can start spinning that motor even without the torque of the motor being. So thermal protection. There's a lot of ways in which a motor can produce excessive heat, like overloading the motor periodically or for just a prolonged duration of time. You can have single phasing, unbalance of the supply voltage. Generally, the insulation's life is halved for every 10 degrees C rise in the temperature above the rated thermal limits. So we need to protect the asset with thermal protection. And you can see here, this is an example, and it's out of the standards as well, the IEEE standard that I mentioned before. And this is just kind of gives you an overall look of the motor starting currents or starting voltages. I apologize. Well, this is actually current here. Yeah, starting currents, and you have 80% and 100%. And then also here's your thermal loading curve. And as we saw before, we're trying to take this curve and match it against the overload. And you also have the motor thermal damage curve as well. So we want to make sure that we coordinate. It's a tight space in there, but we would just want to make sure that we can also get everything coordinated properly and protect it as well. So with the motor, it kind of gives you this. So this is an example here of a thermal element, and then we're using the motor characteristics to actually but we're overlapping motor characteristic inside of the thermal overload. So we want to make sure that we're not operating for normal operating temperatures, but also too, we want to make sure that we're running that tight line where we can actually run this motor to full capacity and use the most that we can out of it. We definitely don't want to false trip it either. Also in the motors, you can use RTD biasing, and what that does is that allows for the measured values to be used in the thermal calculations rather than using a thermal model which uses the nameplate settings. RTD biasing is actually a more accurate way to determine the motor characteristics, because it's an actual sensor that sits inside, is placed inside the motor itself, and it can measure that information rather than calculating it from just the nameplate issues that could be put on the motor nameplate. Thermal protection. So this is kind of a little example how thermal protection works. Get your power, right? We got to get power from the power supply. And once we get the power in from the power supply, we're getting good voltage here. Yeah, looks good. And then we're going to start putting a little bit of power. Current's starting to go. All right, our motor's getting it. Now our motor starts going and it's operating, and it's starting to overheat. And you know, we for protection, we need to make sure that we have protection to prevent our motor from overheating as well. And you know, definitely this is a you know, costing money again. Here it is. But if you know, with the right protection, or you know, not overloading your motor and making sure that you know, good maintenance is done, this can definitely save you a ton of money in the long run. The current and undervoltage protection, I think this is our last one that we'll go over. Usually is a typical starting current is about 6 times FLA. I think I said that earlier as well. So you also have this startup current can be used as a baseline if no other documentation is available as well. And like we were saying earlier, that there's a lot of documentation that you don't necessarily get. Or if you're coming into a new facility and all that information is gone, or you can't find it, or you know, that's always a big headache as well. The typical of the 1% voltage unbalance will equate to the 6% current unbalance as well. So when you're setting this, this is pretty common. When I put on here as typical, is because I've read through multiple relay manufacturer manuals, and most of them are pretty, or almost state very similar to the 1% to the 6. So this seems to be the typical round for this. And then the unbalance equation here is something I pulled from one of the relay manufacturers manuals, and just kind of gives you an overall how simple this can be. The A factor here that it's talking about, here's a simplified version of what the A factor entails, would be pretty much the impedance of this motor itself. A lot of times in the if you don't have this information, then you can actually get just use it set to 1. So this just be a value is just set to 1 most of the time. And again, this looks at the different relay manufacturers manuals, because each relay manufacturer is different, and each one state a different default value to use for their particular setup. And then also we also want to make sure that the relay settings account for the negative sequence currents that could be present but not coming from the motor protective circuit. This could be an external component that could be also seen by the relay. Therefore, the time should be allowed for the appropriate protection to clear it. This will also help prevent unnecessary negative sequence currents from being introduced into the motor circuit and overheating the motor. That's unnecessary, because we don't want anything to affect our motor that we're trying to use. Also, a good thing to point out too is that you can have unusually high unbalanced values, and this can be caused by incorrect phase CT wiring as well. So that can be due to uneven heating into, you know, as we saw before in the negative sequence or phase reversal, we saw a bunch of we almost went 1 per unit in negative sequence currents, and yet that creates a lot of unnecessary heating that we don't need. Oh, wow. Okay, summary. All right. There we go. So this is our product line. At the end of our webinars, we like to kind of show you guys what we have. You know, we do have lots of relay test equipment. We have different varieties and different sizes for all different applications. All these relay test sets have the same software, and we have a lot of the software in these units and test plans that we can use to test motor protective relays. So if you guys are interested, definitely reach out to us. I'll have some information at the end of this webinar. And then here's something I always like to show is in our software as well as you can provide connection notes. As you can see, I have just an old manual I just pulled out of a relay, and you can add connection notes, and you can actually take this screenshot out and you can actually put it into the relay test plan, and that's very helpful. I think sometimes, like it said, pictures give 1,000 words, right? So it's nice to be able to have a note area where you can take a picture of your diagram or how you connect it and input it into your test plan. So a little bit of the summary, motor types and the protection required. So as discussed, there are different types of motors in the NEMA guide, the MG-1 and the IEEE C3796, the guide for AC motor protection. They have a lot of guidelines in here, and they will assist you with the most common failures also that happen to motors, but also what protection elements can help minimize those damages against these faults. The phase and ground overloads and short circuits can produce high daily currents, and it is very important to protect personnel first, and second, the equipment against these types of faults. These schemes have been working for over 75 plus years, and this allows the motor not to get into an overload situation when loads change or internal or external faults happen. Differential protection can be configured in different ways, and make sure that it is wired in the field. What the wiring in the field is the same as what's on the as-built drawings. And what I mean are those are the completed drawings from any substation that should be on record on file, and make sure that the currents are canceling out under normal operating conditions and only operate during abnormal conditions. So it's a good time to kind of test your relay settings as well as you make these. The fourth point here for the phase reversal. So the phase reversal, the motors can create the damage, can create damage to the attached load and to itself if not properly connected. And connected for the correct phase rotation, relays will have elements that will help protect against this issue. Like I was saying earlier, you can just set a phase rotation element, and as soon as it senses the reversal, then it can issue a trip or an alarm, however you wish to configure that. Load loss and mechanical jam. You've seen what that thing can do. That's a nasty guy. But it's just one of the many scenarios that could take place. And most microprocessor relays have an element that's specifically just for load jam, jam trip, load trip. So you can kind of get, they kind of isolated a couple of those elements out for you. In the electromechanical world, you're probably going to have individual relays on a panel, so you're probably going to have a lot of relays in there, but there will be something very similar to just an overcurrent relay that can help protect that. The undervoltage issues that can help prevent a motor from starting, or if the motor's already running and undervoltage issue occurs, then the proper 27 element will need to be set. And the machines, it needs to be set so that way, if you do have an undervoltage condition while the motor's running, that the motor doesn't continually start spinning because of the high inertia of the load itself. So we want to make sure we protect that. The second to last one, the thermal elements are basis for motor protection. So thermal is pretty much what is the basis of the motor, of course, but that thing runs in temperatures, extreme temperatures inside, extreme temperatures outside. It also runs hot with loads. It gets overloaded occasionally. Thermal elements are very important, and it's really nice to have the RTD biasing because it gives you a little bit of better accuracy in what that motor is doing out there. You don't physically have to go out there and take measurements all the time, or you're relying on nameplate information that's used in the thermal model. So we want to make sure that, if you have the opportunity to use the RTDs, I would suggest to do so. And then the last one, but not least, is the unbalancing. Like we said, is everything I've read through is typically about a 1% voltage unbalance, which is, can equate about 6 to 5% current unbalance. So I want to thank everybody for listening to my webinar today. I really appreciate it. And I think Mr. Mike is going to kind of take this away.
Yep. Thanks a lot, David. So at this time, the presentation portion of our webinar is officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or a demo on any Megger product. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar next month, December 18th, titled Low Voltage Circuit Breaker Ground Fault Protection Utilizing Primary Injection Test Method. All right, let's jump into your questions. The first one I have, I'm going to be directing towards Abel Gonzalez. Abel, do paper machines use induction motors or DC motors?
Hi, Mike, can you hear me?
Yep.
Okay, live. Thanks. Mike. Thanks for the question. Yeah, that's an interesting question. I've been thinking about it since I saw it. I want to remind those out there who may be of a little bit older. Do you guys remember what a Ward Leonard system is? That used to be that's an induction machine powering up a DC generator controlling a DC motor. The idea of using 3 machines to control one was because the DC machine, you can control the speed and the torque of the DC machine very well if you're able to control the voltage fed to the machine. And to control the voltage fed to the machine, you use the DC generator. And to move that DC generator, you use an AC machine, and then to control the voltage output of that DC generator, you used to control the voltage of the field of the DC generator. That's a complicated setup, right? Well, it was used a lot because when you needed accurate control of speed and torque of a machine, you went to the DC machines because AC machines are a lot harder, tougher, stronger, easier, but they were very hard to control when it came to proper control of the speed and the torque of the machine. But that all changed in the 80s with the introduction of vector control, and then in the 90s when that went mainstream. And I guess I'm doing this historical perspective because in the 90s there was a huge change where AC machines that we knew what needed to be done to control from the 1920s, but it was not easy to do it because we didn't have the tools. And then with the introduction of proper silicon that we can control and use in inverters, and then the introduction of variable frequency drives, that all changed. What I'm trying to say is that paper machines, you can use them with both DC and AC motors. DC motors are still used because of the fact that a lot of those installations are very old. But if you were to use it in a an environment today where you could choose, I guess the choice would be to use a variable frequency drive with an AC or induction motor. It would be, I guess, perhaps a little bit more expensive than using a DC machine, but it's gonna be way better when it comes to the possibilities of control, maintenance, and whatnot. So I guess that would be the answer to that question.
Isabel? Yeah.
Okay.
Next, I'm going to send our questions over to Sugosh Kuber. Sugosh, which motor type is most common, induction or synchro?
Thanks, Michael. So what we've seen is, usually induction motors are most commonly used when we compare it to synchronous motors. I would say as close as, close to 80 or 90% of the motors that are used in the industry today, they account for induction type. There can be many reasons why, one would be chosen over the other. The way they work is of course different from each other, the induction and synchronous machines. The usage also varies depending on what applications you need them for, right? So, for example, like synchronous motor it's a doubly excited machine, whereas induction motor is a single excited machine. So, like for as comparison, if you compare both type of motors on the same voltage level and of course the same output, synchronous motors are considered to be more expensive as compared to induction. So again, there are various reasons why you would find one more than the other. It just depends on all these different factors.
All right, thanks, Sugosh. Next is over to Abel. Abel, is rotor damage common, e.g. open shorting bars?
Sorry, guys, I was muted. Yes, actually, depending on where you get your numbers, and there are been many statistical, I would say, studies over the years, and the numbers are published by different manufacturers, etc. Between 6 and 13% of faults found in motors are related to the rotor itself. Of those, a significant number has to do with broken bars in induction motors, which is, I guess, where the question comes to. Now, a broken bar in the induction motor is something that could and could not be catastrophic to the motor. It depends on how much load you are trying to get to how much load is connected to the motor, what are the specific conditions under which the motor is operating. An induction motor could be operating with a broken bar and you not know it until perhaps you do some maintenance or you realize that there is a lot of vibration, or perhaps the motor cannot give you enough torque for the load that you're trying to supply with it. So yes, the broken or open bars in the rotor of the induction motor is a pretty common occurrence. I'm not going to say that it's something that happens every day, but when it comes to failure modes, it's one that can be perhaps between 5 and 10% of the failures out there. Okay.
All right, thanks a lot. Next is over to Sugosh. Sugosh, what are the advantages or disadvantages of each of the presented scheme of motor protection by neutral, or for which you should be installed?
Okay, that's a good question. So, like David explained, there are multiple ways of detecting ground faults, in the motor protection. So, the first method would be the zero sequence CT approach. It's highly sensitive. The way this works is, all the phase conductors are passed through a single CT, which is referred to as a zero sequence CT. Ideally, the sum of these currents would result in a zero output, which means it's all balanced. But let's say if one of those phases is shorted to ground, so now the sum of these currents would not be zero anymore, which will create the zero sequence current in the through that CT for the relay to see and trip. right? So this is one of the methods, and so I would say this is the recommended, ideally recommended method. But now again, it depends on the all the statistics as to how large your cables are that you're trying to fit them through the zero sequence CTs. Now let's say those cables are so large that you cannot fit them through zero sequence CT window, then you would have to go use the residual ground fault configuration, right? Uh, so so the residual ground fault configuration is, of course, it's less sensitive than the zero sequence CT approach. Again, it just depends on what you could use the best. So for instance, if you're using a residual ground fault configuration, and let's say that there's motor starting, when there's a motor starting, the currents increase as up to to 6 times of the FLA. Now let's say even if there's a slight mismatch of these CTs combined, with this high current magnitudes that the relay is trying to see, there might be sometimes a false residual current that the relay sees. So the relay may misinterpret this as a ground fault. So you have to be a little careful when you are using these methods in trying to set up the protection. So it depends on the situation you're in, the type of cables you're using in the installation, and the protection you're using. I hope I answered that question.
Thanks, Ghosh. Next is back over to David. David, at your discretion, when should we use the differential protection on the motor?
Okay, that's a good question. Yeah, I didn't state that in there. So a good rule of thumb is voltage levels of motors that are 2400 up to 13.8 kV will be good for the motor protection, or good for differential protection. But really, any motor or voltage size is good for the protection. It isn't normally used for lower voltage motors. But and two, usually you got to add CTs, and the cabinets are bigger, and you have more room to do stuff. So it almost just depends on how far you want to go with the differential. If you want to go ahead and add it to your system, if you have room to add the CTs, if you have room to add all that information, it wouldn't hurt. I mean, it wouldn't hurt it at all. So it just gives you more protection and sensitivity in there. But you just making sure that you can coordinate that differential protection with the other items that you do have would be key. So thank you.
All right. Next is over to Abel. Abel, could you please briefly explain what protection is used against loss of synchronism and how does it work?
Okay. Well, the first thing to, I guess, complete the question is, what are we talking about when we're talking about loss of synchronism? This is something that applies to synchronous motors. Remember that in the synchronous motor, the rotor of the motor is supposed to rotate at the same speed of the let's call it the magnetic field of the stator. So if we have a 2-pole machine, that means that the magnetic field, or the maximum value of the magnetic field of the stator, is rotating at 3600 revolutions per minute. That means that the rotor in a synchronous motor has to rotate at that same speed. And the way that's achieved is by injecting a field into the rotor of the synchronous motor. It's a DC field. It's not created by the external field, and therefore can lock to the external field and still produce torque, right? So if a synchronous motor, if in the synchronous motor the rotor starts moving at a speed that's lower than that of the synchronous field, then you have what's called loss of synchronism. Now, why does loss of synchronism happen in a synchronous motor? The first thing is that it could be simply because you applied to the shaft of the motor a load that's too high for the motor to handle. What happens then is that the motor is going to brake a little bit, so it's going to start moving a little bit slower. The rotor is going to move a little bit slower than the external field. and there you have a loss of synchronism. The load could be so high that it could provoke a stall, or it could provoke the rotor to stop moving at all. Okay. The other reason for a loss of synchronism could be a drop in the voltage supplied to the rotor, because then it cannot produce enough torque, and then you will have the same problem. Motor is going to start losing, because of the fact that it has to try to equal the torque produced, the electromagnetic torque produced by the rotor with the torque demanded by the load. And the other reason, or another reason, could be that the excitation in the rotor, remember that the field that we inject in the rotor is an external field produced by injecting DC into the field of the rotor. Is the amount of energy being injected into the field in the rotor of the motor is too low, then the same thing happens. You will not have enough power to drive the motor at the synchronous speed. Okay, so how do you protect against all that? Well, you have to measure the voltages and currents going into the motor, and that's done by all the relays, protection relays out there. And you have to measure all of the voltages and currents going into the relay, and then you have several options. One of them, I would say one of the more known one, is a protection known as out of step protection. It basically, what it does is it tries to determine the trajectory of the positive sequence impedance as measured by the relay into the machine. If that trajectory brings the impedance of the machine as seen by the relay into the left side of the impedance plane, then you detect a loss of synchronism, and you can either trip or alarm, or depending on what you feel like the conditions of the operation have to be. Another thing that you can do is you can use a power factor relay, and I'm only going to mention these two because there are probably 15 or more different methods of detecting this, but I guess these two would be the most popular ones. And on the power factor side, it's not only the power factor, you could measure the power. Now, remember that the synchronous motor is supposed to operate at a power factor that could be either unity, a power factor of 1, or a power factor between 0.8 on both sides, either leading or lagging. If the power factor of the machine, remember the power factor is what? If the power factor is the cosine of the angle between the voltage and the current, or the cosine of the angle of the impedance as seen at the relay, or the impedance, the apparent impedance that the motor represents for the relay that's measuring the voltages injected into the motor and the currents that are being taken by the motor as a load. So if that power factor goes beyond that 0.8% that we're talking about, then we can declare a condition of loss of synchronism. However, that may not be, that may be like something too tight. So maybe the adjustment, the setting for that number, you may not want to use 0.8%. Maybe you want to use a higher value on both sides. And the thing is that with power factor, you have active power and apparent power going into the motor. When the motor power factor changes, also the amount of reactive energy that the motor takes changes. Remember, if it is a synchronous motor, it's supposed to take very little or no reactive power from the system. When the amount of reactive power taken by that synchronous motor becomes too high, then you have what's called an asynchronous operation, which again is the consequence of the loss of synchronism in the. So that's another option that you have when it comes to protecting against the loss of synchronism. Like I said, I'm only going to discuss these 3 options. There are many out there that you can find. Okay.
All right.
Okay.
Wonderful. And while I have you, Abel, the next question is going to be sent over to you. Does NEMA MG1 only apply in the USA?
Well, actually, it applies wherever the NEMA MG1 is adopted as a standard. It is a standard that is originated in the USA by NEMA, the National Electrical Manufacturers Association, and it's adopted all over the United States. Here in Canada, it's used in places like Mexico, for example. But again, it depends on whether the national standards body of the country that we are talking about decides to adopt NEMA or parts of NEMA, which is something that I know that happens. Sometimes the standards are not adopted in its entirety, but only the part of the standard that wants to be adopted in a particular place, and some places have their own standards. Okay.
All right. Thanks a lot. Next is over to Sugosh. Sugosh, with regards to motor differential protection, do you compensate for any CT lead length differences to the protective relay, or is this compensated by a small slope value?
Okay, so when we talk about the CT lead length, it's proportional to the resistance of the leads, right? And so the resistance of the leads it affects the burden, which can in turn be a reason for the saturation. So in one way, yes, it is compensated by the slope value you choose. The reason I say that it's compensated by the slope value you choose is that the slope characteristic, it's used to prevent improper operation of of the scheme, any time it sees external faults, right? It only has to trip for internal faults, and these imbalances that you see in the system, they can be caused because of CT accuracy errors or CT saturation. So the slope that you design takes care of these errors, or the accounts for these errors. The slope characteristic, it allows for being very sensitive when the fault current is really low. And if you have a relay where you can have like a dual slope characteristic, now the characteristic would be less sensitive on the second slope where the fault current is so high, and because the CT performance can produce incorrect operating signals for the relay.
All right, thank you, Sugosh. Next, back over to Abel. Abel, I noticed that one of your motor nameplates was showing an altitude reading. What is the purpose of this if you have an ambient temperature reading?
Well, the thing is that the ambient temperature reading is a number that is given at a particular atmospheric pressure of 1 atmosphere, or the atmospheric pressure at sea level. What happens at higher altitudes is that the air becomes thinner, and most of the heat leaves the motor, because there are various ways in which the heat is transferred from one body to another, one being conduction, 2 bodies in touching each other, the other one being radiation. The heat is being radiated via electromagnetic waves, photons leaving the machine. But the third one, which is the most important for the motor, is convection. Convection means air getting into the motor and being pushed out of the motor by the fans. However, convection is more efficient when the medium that's used to produce that convection is thicker. It has a higher density, because then you have more amount of heat transferred per unit of time. What happens at higher altitudes is that the air is thinner, which means that the amount of heat transferred out of the motor because of that process is going to be lower, and then you have to derate your motor because it's going to be able to dissipate heat less efficiently because of the fact that it's using the convection mean, which is the air, is going to be less efficient at that higher altitude. That is the reason why you use altitude. As you say, this motor is rated up to this much altitude. For higher altitudes, you need to either increase the number of fins that you have in the fan, increase the size of the motor, work it on at lower temperatures. You have to do other things to work motors at higher altitudes. Okay.
All right, thanks a lot. Next is over to David. With reference to slide 30, is it recommended practice to ground the CT outputs at both ends of the motor differential scheme? Is it not the practice to ground only at the relay in the substation, especially when the power cable is long, say 100 meters?
So right now, the slide you're showing is what? You should be able to see my differential slide. Is that correct?
We're on the differential slide.
Awesome. So this is the slide that was referenced in this question is number 30. So what we're showing here is we're just kind of showing in this diagram, it's just showing the YY CTs, right? And they're going to be connected in YY with one side going to ground here, right? So the question is was it practice in doing the ground the CT outputs on both ends? Is practice not to ground only in the relay substation. So this actually can be grounded at, there's going to be a terminal block or some type of marshalling cabinet that's going to be where these dotted lines are in this diagram that connect to the relay. So this is going to pass through some sort of a terminal block and then probably go into the house, into the substation. Now these grounds, it is good to have these grounds in at the relay where you have one grounding point for your CT circuit inside the control house. But what happens sometimes too is you don't have access to a lot of these different grounding points. So sometimes you have to ground it outside in the marshalling cabinet, which could be outside in the yard or in a pass-through or in a vault underground, however that happens. So really it's as long as you don't have two grounds on the same current circuit, you're okay. But what would be a good idea is to make sure that you can have access to these, to visually looking at this ground wherever that connection's made. Because if you're in a troubleshooting scenario, then it's nice to go see where these connections are actually made, and you want to be able to put your eyes on them so you can verify them. If these things are hidden somewhere, then it of course, it just makes life a little bit more difficult at that point. But yeah, you can. There's not really a set. Do I need to ground the yard? Do I need to ground it here? What we want to do is just make sure that we have access so we can see it and make it to where it's only grounded once per CT circuit, and we don't have any double grounds in here. So there we
go. All right, thanks, David.
Yeah, you're welcome.
Next to Abel, is there a requirement for the CTs to be calibrated annually?
Well, the requirements that you have to follow depend on your local regulations. That said, it is a good idea to check your CTs regularly. What I mean by that is that you should have, as part of your maintenance schedule, you should have the checking of the CTs as part of regularly. I mean, with either 1 year, 2 years, or whatever your local regulations say. You should be able to meet that for various reasons, not just to fill a requirement, but because CT's characteristics change, the burden connected to the CT changes as the installation ages. Your connections become rusted, they become loose, especially in a motor scenario where most of the time you are in a place where there is a lot of let's say vibration, there is a lot of contamination and things like that. And so it is a good idea, even if your local regulations say that you should have, I don't know, this much time for CT checking. Maybe it's a good idea to, because Your CTs are the eyes that you have into the operation of the motor, both CTs and PTs in the cases where you're operating with motors which voltage level requires you to use potential transformers as well. Those are your eyes into the operation of the motors, and your protections are only going to be as good as your primary transducers, which are the CTs and PTs. Okay, so I would be that. I'd say that that's the question.
All right. Thanks a
Or the-
lot. Yeah.
So,
So Sughosh, how could we test a thermal protection?
Okay, so the way like David explained earlier, is all this thermal overload element in a relay, they are built on the basis of some thermal overload curves. They define how this element would behave whenever it thinks it sees a overload condition on a motor, and these are dependent on the equation, I squared T times R. So what it means is that you would be injecting currents to the the phase terminals on the relay. So depending on the magnitude of the current and also how long this current is being injected to the motor, the thermal element in the relay, it's going to see that the current is increasing for this much amount of time, and it cross checks with the overload curve that is set in the relay. So that is how you would test a thermal protection element. And of course, you would have to be careful when you test different types of motor protection relays, especially the thermal overload elements. If it's a microprocessor relay, or if it's a electromechanical, or it's like a bimetal overload relays, because if you are going to test multiple points, you have to make sure that the relay is the element is cooled down, especially if it's like a bimetallic style of relay, before you can try your second test. But yeah, this is a basic idea to perform this test, is to inject the current based on above the setting, and for a particular amount of time when it meets that point on the overload curve for the element to trip.
All right. It looks like that's all the time we have for questions today. We apologize if we didn't get to yours live, but we will be working to follow up with you offline. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great weekend.